Welcome to my tutorial over implementing recursive descent parsers in Python. To begin with, I'm going to have some preliminaries. First, I assume that you guys have knowledge about grammars and finite automatons. Secondly, I assume that you guys have knowledge about Python programming. And thirdly, I assume that you guys have knowledge about basic data structures. So to begin with, a recursive descent parser is known as a top-down predictive parser, where top-down simply refers to the fact that the derivation tree derives from the top down, and predictive simply means that it predicts the next token before consuming. It is also an LL1 parser, where the 1 denotes how many lookup items it needs to predict before consuming, and LL simply denotes that it uses a context-free grammar, where a context-free grammar is a grammar that uses recursion in basic terms. So to begin with, here's an example context-free grammar for deriving simple equations with addition and subtraction. So here we have two productions, start and operand, where start and operand are called non-terminals. And number, the addition sign, and the subtraction sign are known as terminals. And so let's go through an example derivation given the following input, 3 minus 5 plus 3. So to begin with, start derives start operand number, where start itself is start operand number. So this start symbol deconstructs into start operand number, where operand number follows through. And start is also a number. Just in case you didn't know, this vertical bar denotes the OR symbol. So an operand is a addition or subtraction, and a start is this expression or a number. So back to our derivation. A start operand number, where this start is now a number, as we see from here. And then from here, it's straight a linear correlation. We go from number to 3, operand to minus, number to 5, operand to plus, number to 3. And the derivation tree of this is the following. Now this is a linear fashion, while here we have our derivation tree. And notice how it starts at the top and it works down. This is known as a top-down parser. And here is an example of a bottom-up parser. Now this is a different example. This is one I found in my textbook. But simply start at IDA, this is the beginning, and it works upwards. So instead of working down, it predicts and it works upwards into a bottom-up parser. So now we have this grammar, and you can see how this derivation tree is derived. How would you actually implement this in Python, for example? Well, first off, I'm going to give you some basic pseudocode and implementation. So for each production rule we have, there is an equivalent function. So we're going to have two functions, start and operand. And so first off, we're going to begin with the start function. So the first thing first, we're going to have the start, we're going to store it in first, then we're going to get the next token, and we're going to say if that token is an operand, as we see here, then we're going to get the next token again, store in value. If the next token, value, is an operand, is a number, then we're going to return operand of the first, the value, and the token. All right? And so now we go over here to the operand function. We're given left, right, and operand. Left simply refers to the left-hand side of the operand. Right refers to the right-hand side of the operand. And the operand refers to the minus sign in this example. So we're just going to return 3 minus 5. So then we will return 3 minus 5, which would be negative 2. And then we return negative 2 from here. And this would be an example derivation of this and implementation for pseudocode. If you haven't noticed, first off, we have the start symbol, and we have the start function right here. So if we were to call start the first time, it's going to call start again, which is then going to start here, and it's going to start again. It's going to call start, and we're going to enter into an infinite recursion. And this is because our grammar is left recursive. Left recursive grammars are denoted by the fact that the production or the terminal and the non-terminal start is the first symbol on the right hand side. So because start is the first symbol on the right hand side of this left expression, it is left recursive. And we can even see that in our derivation tree. We can see that we recursively go down to the left. And this is a problem for recursive descent parsers. We want to get rid of this. And so here, the problem has been relieved, and now our grammar is not left recursive, it is right recursive. And just for the simplicity of the video, I'm not going to show you guys how this was performed or done, because I assume that you guys know about grammars before to begin with. So here we have our new context-free grammar, and we have our old context-free grammar. So what happened was, instead of calling start again, we introduced a temporary terminal called term. So now we have number, term, where term is an operand, number, term, or epsilon. Now notice how term is on the right-hand side of the equation. This is because we translated our old our old grammar from left recursive to right recursive now. An example derivation of, let's say, 3 minus 3 plus 3 is the following. So we start off here with start derives number term, where number is 3, and a term is an operand number term. So term decomposes into this. We consume operand, we consume number, term again is an operand number term. So now we have operand number term, consume operand, consume number, we have term. Now we have an epsilon transition. Epsilon transition simply means that if it's not an operand, we skip. So now we skip, and we've reached the end of the input, and here we have our full derivation. And the derivation tree for this is the following. So here we start at start, we work from left to right, and notice how it spirals down to the right. This is because our grammar is now right recursive. An example pseudocode implementation of this grammar is the following. So we'd start here, we would begin at start, we'd get the first token. If the token is a number, we return the term of token. And here at term, we get the next token, which should be an operand. If operand is actually an operand, if it's not, that means it's an epsilon transition, and we just return the previous value. If it is an operand, we get the next token, which should be a number. If it's not a number, then we have an error. This would occur, for example, if someone was to insert 3 minus instead of a 3 minus 3 or 3 minus 5. So then we store the product of our previous tokens inside of temp by the use of the operand function. So we pass in previous, we pass in value, and then we pass in operand. And then here we simply perform a left operand right, just like before, except that this time, instead of returning this value, we return the term of this value. And this allows for a recursive right-hand side. So now I'm actually going to give a working Python implementation of a recursive descent parsing algorithm for a calculator. So here we have our basic calculator grammar. And to begin with, we need to decompose our input into tokens. And that is through the use of what's called the scanner. So first we need to scan our input and tokenize each of the components. And what a scanner simply is a finite automaton. So here we have an example of a finite automaton for accepting numbers. So this would work for any kind of integers or floats. So we're going to loop on an initial state on integers, and this would work for integers. And then let's say if we have a decimal value like 0.5, we would loop on the 0, and then on the decimal we go here and we'd loop again. And this makes sure that we don't have any repeating decimals and such. So to begin with, I'm going to define a class called token. This way we can actually store our tokens inside a structure. So here we're going to define our token and our value of the token. So what we're going to do is we're going to decompose our input into two parts. So let's say we have 3 minus 3. We're going to decompose this into a token, the token value of 3, which would be num, and then the value part would be 3, and then given the minus, the subtraction symbol, the token part would be operand, and the value would be minus, and then for the last, let's make this 5. For 5, the token value would be num, and the value would be 5. This way we can store the input into an equivalent way for tokens. And once we break down all of our input into tokens, we need to iterate over them. And in Python, you can use what's known as an iterator. Well, the problem is our grammar is LL1, if you remember, which means that it needs to peek ahead at the next value without actually consuming it. And in Python, the native iterator class does not have a peek function, so I'm going to actually define an iterator myself. So we're going to call this class iterator, make our initial function, scroll down a little bit, and we're going to have our input. I'm going to call this array. So this would be our array of tokens. So we decompose this into these following tokens, and then we'd store that into a list, which would be our array. Let's call this list actually. And then I'm going to make this a private variable, private attribute. And then we're going to store the length of the list as well. And we're going to store the index. So just like in C and other programming languages, we can iterate through an array using an index, just like in Python. So we're going to store this. The next thing we're going to do is define a next function. This is going to retrieve the current value and iterate to the next. So first, we need to check if the current index equals the length of the list. This way, we can make sure we're not reaching an out-of-bounds statement. And if this occurs, we're going to return none. And if it doesn't occur, we're going to first update the current index by 1. Next, we're going to return the value at that said index. So this time we're going to go -1. This is because we want to increase the index but return the current value. So for example, let's say this is the first next call. The current index is 0. We're increasing it to 1, but we don't want to return the array at the 1 index. We want to return the array at the 0 index. This is why we -1. And then our next function is peek. Peek does the same thing as next, except this time, instead of incrementing the index, we just return the current. So this is going to return index at 0 without incrementing. And this is all the time I have for right now. And next time I'm going to actually implement the scanner function. That way we can actually tokenize our input.